All right, we'll jump right in. We're finding the stomach. All right. All right, so facts about the stomach. Think of it as a food blender. I mean, a very slow food blender. It takes a few hours to blend your food into kind. And also think about it as a reservoir where the gastric juices mix and digest the food. It's very distensible. It can hold up to 2 to 3 liters of food, whereas a newborn stomach can only hold about 30 ml of food. And its primary function is chemical digestion, where all the acids and enzymes, the pH can really get really low, down to 1 or 2. All right, well, so we'll get into the details of the gastric juice, but the anatomy is, we got a few pictures here. So, if you were to remove this organ from the body cavity, what you got to do is cut at the esophagus right there. And you cut around the duodenum right there. And you have to cut along the omentum off, the greater and lesser curvature. And you get this view here. And we can learn the regions of the stomach. The regions include fundus. That's that superior round part. For example, if you drink carbonated beverage, you can see all the CO2 bubble up in that region in imaging. It's a small portion of the stomach. You see the cardia. Named so because, well, the heart sits right on top of it. Hence the name. Now, as you can see, the majority of the stomach is the body of the stomach. I'll just describe it as the major portion of the stomach. However, as you see the narrowing of the body into the pyloric region, or the pylorus, it's a word that means gatekeeper. The gatekeeper function, well, you can't see it in this picture. There's a very strong, powerful sphincter. It's called the pyloric sphincter, and so note that. guards the duodenum from receiving too much acidic chyme at once. Guards duodenum. From receiving too much acidic chyme. So it's basically the end of the stomach. One functional thing is when food kind of gets pushed towards this end of the stomach, if food is not fully digested, for example, if there are undigested proteins in the pyloric region, the gastric glands in the pyloric region have these enteroendocrine cells that will secrete more gastrin hormone to facilitate better juice secretion and digestion. So let me put this. Gastric glands in this region only, I mean there are gastric glands in all the regions, but gastric glands in this region have enteroendocrine cells. Enteroendocrine cells. Sometimes I just call them G cells because they secrete the hormone gastrin. That secrete gastrin. So we'll talk a lot about a gastrin today. The gastrin is one of the chief hormones that facilitates the secretion of gastric juice. I mean, that's the anatomy, just the four regions, right? I'll talk about the function coming up. And we also know the curvatures that I've also mentioned, greater and lesser curvature, because the greater and lesser omentum, that's how they got their names. I'll just put it up here. Greater and lesser curvatures. All right, so if you start to dissect and remove the layers of the stomach wall, you know, like the outermost layer, and oh, by the way, this color is, that's a pretty accurate illustration of the coloration of the stomach when, you know, you see it in a fresh cadaver. And it's the outermost layer of the GI tract wall, which is the serosa adventitia. Remove the serosa, you can start to see the muscle layers. The muscularis externa in the stomach has 3 layers. Usually it only has 2, but here we have 3. In the stomach, muscularis externa has 3 layers. There's the innermost oblique, circular, longitudinal layers. Oblique, circular, longitudinal. So the correct way to name it, not practical, oblique layer of muscularis externa. And I named the other ones the same thing last time. Well, let's take a look at them. So the outermost, going from outer to inner, See how the direction of the fibers run in this outermost layer? They're running longitudinally with the stomach. But this layer on the inside of that, it's running circular. And then oblique to that is the innermost oblique layer. So look for those on models. They're usually shown. Okay. There's the serosa up there. Okay. So they usually show the serosa and then all 3 layers of muscularis externa. And because they got it windowed open here, that's the sphincter. When sphincters contract, they pucker and they shut. You got a sphincter on that end, that's a strong sphincter. There's a weaker sphincter up here. Okay, when this sphincter fails and you get acid reflux up there, that's heartburn. You can see the endoscope there, and you can take a view there to see if you have an ulcer or not. In this view here, you completely see the internal view of the stomach. I said earlier that the stomach can expand, it can stretch, it can distend to hold 2 to 3 liters of food. And the wrinkly appearance, when it's empty, those folds are called rugae. So note that. These longitudinal folds called rugae. That model's over there, and well, you can see the rugae over here, and you can see how they model the serosa, that layer there. And then when they strip it away, it's hard to see on the picture, but there are longitudinal fibers running on this edge there that they show, and that's circular, and that's the innermost oblique layer. So the stomach, when it is full of food, there's these peristaltic waves, about 3 per minute. Write that down. Peristaltic waves occur 3 per minute. So look what happens with each wave. You get propulsion. You're just pushing food toward the pyloric region. Then the grinding. This is the most vigorous peristalsis and mixing occur here. The pyloric end of the stomach acts as a pump that delivers just a small amount of chyme into the duodenum. Again, that valve is slightly open during this time of the peristalsis to allow just a little bit. The stomach can accommodate a lot of food stuff, but the duodenum cannot. Okay, so it's very important that you just allow just a few mils at a time. And then this retropulsion. Okay, the retropulsion, the peristaltic wave closes the pyloric valve, forcing most of the contents backwards. Okay. So valve slightly open, valve closed. So the valve is closed on steps 1 and 3, and it's only slightly open during the grinding phase. So peristaltic waves occur about 3 per minute, and so in each of those you get propulsion, grinding, retropulsion. The only one where the valve is slightly open is this one. So this phase, I'll say squirt, a few mils, past pyloric sphincter. So when you're done eating and you feel full and you're waiting for your food to go down, you're literally waiting for it to go down. You only squirt a few mils at a time to the duodenum. All right, well, anyways, how is this acidic chyme generated? How are all these gastric juices stimulated? Now, I'll spend a lot of time talking about it. That's really the physiology of the stomach, the regulation of gastric secretion. gastric secretion is vomit. Okay, I mean, vomit's disgusting, it stinks, you know what it looks like, but that's the job of the stomach. Well, okay, so the regulation of gastric secretion occurs in these three phases. We call it head, stomach, small intestine. Gastric secretion. So whenever you read about this in the book and they use the term gastric juices, what's the juice? I want you to start to think of the gastric gland that are in the stomach mucosa. Secreted by gastric glands, mucosa. Remember, you got mucosa, submucosa, muscularis externa, serosa. But in the innermost layer, the mucosa, we'll look at it more closely. But for now, what you can see on this picture is those gastric glands, the principal cell types that secrete stuff are mucus chief parietal cells. That's how we know that. All right, so the gastric juices, they're controlled by neuronal and hormonal mechanisms in three phases. The first phase, I said head. It's on your head. You're hungry and you think about food. Okay. I'll list that one first. It's on your head. I'm hungry. What my son always tells me. And just the thought of food, or for example, if you're hungry and you go to the restaurant, you get out of the car and you can even smell the food from outside in the parking lot. You go inside and you smell the food more and you look at see what people are eating. You see the server walk by with a tray of food. Oh, that was good, and all of that really gets the juices flowing, as I say. And then we'll talk about the gastric phase. Well, I have other slides. Let me just show you the pictures here. All right, so this head phase here, just the mere sight, taste, aroma, or thought of food triggers this reflex. It's brief, it's for a few minutes, but you start the process. So they show an empty stomach because you haven't started eating yet. But these are the cells of the gastric gland that you should know for the quote-unquote I'm hungry. So the gastric glands get going. So let's note these cell types. Mucus chief parietal cells. Well, it's obvious that mucus cells secrete mucus. Mucus is very important for the stomach. It's a nice physical barrier between the epithelium and the HCl. Keeps you from getting an ulcer, although people do get ulcers. That's something you could Google and look at. Bleeding ulcers, they're really disgusting to look at, but it's a failure of the stomach lining to protect itself. And the stomach acid kind of dissolves the mucosal layers. Then you have the chief cells, and these cells secrete pepsinogen. Now, pepsinogen is an inactive form of an enzyme. Think of peptide bonds. Those hold amino acids together. So what does this digest? Protein. So for that reason, chief cells are sometimes called peptic cells. Here, if you ever seen that term. Peptic cells. I mostly call them chief cells. Now, parietal cells, they look like these fuzzy pitchforks. They have this trident or letter E shape and then drawn in. Well, anyways, they secrete the acid. They also secrete that intrinsic factor I mentioned in another lecture. Intrinsic factor, it helps you absorb vitamin B12 and iron. But anyways, those come. I want to focus mostly on the acid. Those are the acid secreting cells. So these are the cells of the gastric gland, and well, what do you think the most numerous cell is? The one that's called chief cell. It's the chief cell, it's most of them. And I also mentioned in one particular region you also have, remember the G cells? So I'll list them down here, G cell, or enteroendocrine cells. They secrete the hormone gastrin. That was in the pyloric region only, as far as I know. Okay, wait. You got the juices flowing, okay? Just thinking about it. Or sometimes you like to order appetizers when you go to the restaurant, right? So the idea behind starters, appetizers, is just a little bit of food also helps this. You get the gastric glands going, oh, when I order appetizers, I just get full, and I don't have room for the main course. I don't eat very much, but that's the thought behind a little bit of an appetizer to get this going. Then let's fast forward to, this is like, you're basically almost through eating, and you're really full. Okay, but you keep piling the food down, right? So I gotta finish this. Or you just get a doggy bag. But we call this the gastric phase, and they show you a full stomach, and they show you the gastric gland in full effect. So there's a lot going on here. Let me kind of break it down for you. So this is the gastric phase where most of the juices are secreted. Okay. During a meal, you're eating the main course. And one thing is, as the food comes in, it stretches the stomach. They call that distension. Two triggers. One is neural. Okay, because distension. Stretch the stomach because you're eating a lot of food. A whole plate of food is going down your stomach. Okay? And the other thing is, if there's protein in the food you eat, protein tends to elevate the pH a little bit. Well, anyways, those two things, it stimulates physically the stretch receptors and chemoreceptors to stimulate the gastric gland activity. That's kind of what they're showing you there. So that's kind of the neural trigger. So distension triggers stretch receptors. Chemoreceptors. Well, anyways, those detect those changes of stretch and elevated pH. And what it does is it triggers the release, because it's a neural response, the release of ACH. So ACH is a neurotransmitter that can stimulate those cells that we listed. Okay, so these two things, basically, think of the neurotransmitter ACH, which will stimulate the gastric gland. I don't want to rewrite them, but the same cells, the mucus cells, the chief cells, the parietal cells, and their secretions. The other thing that's happening is a hormonal trigger. As food reaches the pyloric region, undoubtedly there will be some partially digested proteins, partially digested peptides, and that will be a trigger for the release of gastrin from G cells in that region. So two triggers, one is neural, the other is hormonal. So hormonal is when partially digested proteins reach pyloric region, that's a stimulus for release of gastrin from G cells. So what gastrin does, as you can see, that green line, it'll stimulate the chief and parietal cells for more juice, HCl and pepsinogen. So I'll put under gastrin, it'll stimulate chief cells and the parietal cells. It's a few hours long, and this represents 2/3 of all the gastric juices secreted during this phase. So let's take a closer look at the gastric gland now, since we don't really see it in that figure. But in this figure from the Marriott book, look at the top, the mucosal layer is pitted, and it has those glands. So what you're seeing there at the top, surface epithelium, on gross dissection, you just see the rugae, but if you take a really close look under a microscope, you can see that the epithelium is pitted. They're called gastric pits. They're like a bunch of little gopher holes in there, all these little pits. But what they show you here is that those pits, they lead to a few to several glands. Let me draw a few glands there. So that there, what I'm illustrating, will be the gastric gland with those chief parietal mucus cells. And that's the pit. So differentiate gastric glands here versus gastric pits in the surface epithelium. I mean, out of the pits, you'll squirt all the gastric juice, okay? But the cells that do the work of making the juice are in the gastric gland. And, so if you just look at the mucosa, you can see that there's this neck region which has some mucus cells. This pit is just a pit. But you start to get the secreting cells here. And deep in the pit, shown here, you can see our cell types. Our fuzzy pitchforks, the parietal cells. The purple ones are the chief cells, they're the most numerous. And if it's the pyloric region, you have the gastrin secreting cells. I call them G cells sometimes. This book tends to call them enteroendocrine cells because they secrete a hormone, gastrin. Now, the fuzzy pitchfork cells are kind of interesting to look at. There's a slide of them here. And what they show you here is, note that for the parietal cells, the proton, the hydrogen ion, and the chloride are secreted separately, and they form HCl in the lumen. So you secrete the hydrogen ion, chloride ions, the parietal cell. And they form HCl in stomach lumen. So to go back one slide, what it shows you is another thing about that HCl is the HCl is a trigger to activate inactive pepsinogen. Look at the top there, it says pepsinogen that's inactive, but with low pH, it'll be converted to an active form, pepsin, and that can help digest proteins. So, stomach at rest, say in between meals, maybe the pH is something like 4 to 6. However, when you're eating and you get this acid production, stomach, I'll say active, I guess, not rest. You're stimulating those gastric glands, like I told you. When pH becomes less than 3, this is when you get the conversion of pepsinogen to pepsin. Pepsinogen, inactive, what I'm writing here, is converted to pepsin. That's the active form. With the low pH, or less than 3, 2 or 1, right? Something like that.
So low pH triggers.
Yeah,
Okay.
the low pH, and by definition, less than 3 would be low.
Okay.
So people have a problem with acid reflux. I guess the drug of choice are those proton pump inhibitors, and you can see them here, right? I remember I had to take those, and I didn't like it. I think they made it worse because I couldn't digest my food because I was inhibiting these cells, and well, that was my personal experience. But usually that's what they'll prescribe because you're producing less acid. But that means you can't digest your food as well either. So it's kind of like this delicate balance you can talk about with your doctor. I want to move on. This slide is showing you that physical and chemical barrier to protect you from getting an ulcer. In the lumen of the stomach, low pH, say around 2. But then you got that mucus layer, which is the physical barrier. But because there's something called the alkaline tide, where you're getting a lot of bicarbonate. I didn't mention it on this line, sorry. But that alkaline tide, when you're increasing the circulation of bicarb, it ends up here. And so you have a physical and a bicarbonate chemical barrier that helps guard against autodigestion or stomach ulcers. So at the cell surface, it's pH 7. So it's very important that you have this, of all that acid that's being secreted by your stomach. You can help by, don't eat so much. Slow down, chew your food, things like that. I mean, you can help yourself. Stop eating when you're 80% full, not 100% full. Little things like that can help maintain this. So you have a chemical, it's bicarbonate. And then a physical mucus. So these guard against ulcer. All right, so now you're done eating, and you go to the couch, you just sit down, you let your food go down, you digest, and well, you would consider this the intestinal phase. The whole idea is just kind of put on the brakes. You stop eating, and you try to get the stomach to slow down its churning so you don't squirt too much chyme to the duodenum too fast, because it can't handle very much. And the duodenum has all of these intestinal enzymes that it secretes to help further digestion and inhibit stomach motility. And so basically what you got to know are all these hormones right there, and their function and what they target. So let's kind of go through them in the intestinal phase. So for intestinal phase, you may get some gastric juice secretion, but for the most part, you're trying to inhibit the stomach. You may see some gastric juice secretion. Primarily, you're trying to inhibit stomach activity. Because the intestine, it can't accommodate very much. So by trying to get the stomach to slow down, it's like you're pacing the stomach from emptying too fast into you. And so you have arrival of things to the next part of the digestive tract, the duodenum, which is the first part of the small intestine. And well, it depends what's arriving, what's in the chyme. The product of an active stomach is acidic chyme. So the product of stomach, digestion, acidic chyme, what I said earlier is basically vomit if you can't hold your food down. So the arrival of chyme to the duodenum will trigger different intestinal hormones. Arrival of chyme to duodenum. And so what's in the chyme? For example, if there's lipids and maybe some proteins in the chyme, it depends what you eat, right? So lipids, proteins, that will trigger the release of cholecystokinin. That's a word that means move bile. Okay. Chola means bile. Kinin means move. Well, anyways, I usually just call it CCK for short. And well, they show it right there. That's one of the principal things that are secreted. What it's going to do, it's going to target this little green bladder, the gallbladder, to contract. The gallbladder is responsible for storing and concentrating bile. So you squeeze that thing, you're getting some concentrated bile to help empty into the duodenum. So you're going to target, I'll say gallbladder contraction. Also, you're going to target the pancreas. And it'll be stimulated to release all these pancreatic enzymes. Pancreatic enzyme. I'll define the enzymes later when I get to the pancreas. So one thing here is, we'll look at the gallbladder later, but if you're going to squeeze out one end, this little sphincter right there that lets it dump into the duodenum, there's a sphincter there that you got to relax. So you squeeze out one end and then relax the sphincter at the other end. That way the bile will move. Because if you squeeze but you don't open the valve, so to speak, yet the bile's not going anywhere. So that's the other thing this hormone does. It relaxes something called the hepatopancreatic sphincter. So know the actions of these hormones. That's the physiology part here. Well, that's the first one. You know what? I'll list the second one as secretin, because CCK and secretin, those are the two biggies. I'll talk about the other ones I have listed here, but let's talk about secretin next. Well, what you see here, just the arrival of chyme itself is a stimulation for the release of secretin. And listen to the name, secretin. It's a hormone that makes things secrete. We're talking about primarily liver and pancreas. Your liver and your pancreas, those are your two major accessory organs of digestion. The arrival of just chyme itself, that will trigger the release of secretin, and these are all hormones being released from the small intestine. What secretin will do, again, it'll target the two biggies. Liver, it'll make the liver increase the bile production. I mentioned the gallbladder. The gallbladder doesn't produce the bile. It stores the bile that the liver makes. But the liver is the actual bile producing organ. So you get that, and also it'll stimulate pancreas to release some bicarbonate-rich juice. Pancreatic bicarb HCl3 rich juice. That'll help neutralize the stomach acid that's coming. All right, that's secretin. So let's talk about the other ones I have listed there. GIP, gastric inhibitory peptide. Let's see. Well, if you have lipids and or glucose in the chyme, okay, those things will stimulate GIP. Well, one of the things I'll say is GIP, it's named gastric inhibitory peptide, so it helps to inhibit the stomach churning and the stomach gastric glands. Inhibits churning and inhibits gastric glands, but it also will stimulate the release of insulin. All right, then the other two I have listed are VIP and Gastrin. Now VIP, again, is just the general stimulus for its release is just overall chyme. I'm going to abbreviate it VIP. That stands for vasoactive intestinal peptide, and what that'll do is, well, just like it says, it'll dilate the intestinal capillaries, so you increase the blood flow for absorption. Increase, I'll say dilate, intestinal capillaries. For increased blood flow for absorption. Remember, absorption, that's the key function of the intestines. And I call this the food coma hormone, right? And you get tired, all the blood's rushing to your intestines. Then the last one I have is one we mentioned before, gastrin. Gastrin is secreted in the pyloric region of the stomach, but it's also released by the small intestine too. If you're eating too fast and partially digested proteins are making it to the small intestine, you need to release more gastrin. So, partially digested proteins. Those will release the hormone gastrin. Gastrin will actually produce more stomach acid. It'll stimulate gastric glands. Gastric glands. Gastrin is the only hormone that stimulates more stomach activity. You should note, all the other ones I listed, VIP, GIP, secretin, CCK, they all inhibit stomach activity. Okay. You just write in your notes, okay? You show it here, but I already erased some of them off the board, but you can look them up. The goal here is to inhibit the stomach. Gastrin is the only one where you're going to increase the stomach activity because it's like, I guess you ate too much, you didn't chew your food, and partially digested proteins are making it all the way to the intestine. That's not good. All right, so the duodenum itself, we're going to move away from the stomach now. And I'm done talking about the gastric juice secretion. Are there any questions on the gastric juice or any of the hormones that we've listed here? So I'm just moving down the digestive tract from stomach to the small intestine. The first 10 inches of the small intestine is the duodenum. Shown here. So look at that picture and try to figure out everything that's been removed, and I'll walk you through it. Do you see a liver? That's gone. They removed the liver. Do you see a stomach? That's gone too. In fact, you can see the pancreas, which is located behind the stomach. There's the duodenum right there. They cut the transverse colon. There's the spleen. There's the cut end of the stomach there, and that's the inferior vena cava. In fact, those are hepatic veins that will drain into it. But the liver's gone. So anyways, that's what we're talking about there. So let me read what I have on my slide. This is the first 10 inches of the small intestine. The pancreas is its most intimate relation. All but the first 2.5 centimeters of the duodenum lie retroperitoneal. So basically, how it goes in digestion is things are intraperitoneal, then they go retro, then it goes intra, then retro, and it alternates. The stomach is intraperitoneal, but the duodenum, it goes retro. And then here it pops back intra. So I'll say duodenum is primarily, it goes retroperitoneal. Now, you don't have to know those 4 parts, but I will have you understand that in that D2, in that descending part, which is right around here, you're going to have that little spout where the liver and the pancreas can secrete their digestive juices into the duodenum to mix. Now, I use the term hepatopancreatic ampulla there. Before I said you relax the hepatopancreatic sphincter. That ampulla has a sphincter in it. Okay, so that term, that anatomy term, goes by different names. pancreatic sphincter. The sphincter is an important term. That smooth muscle that's relaxed by CCK. Sometimes it's called major duodenal papilla, because it looks like a nipple-shaped structure. And I put major in parentheses because sometimes it's just called duodenal papilla. But anyways, it's a little spout that's in the duodenum, and the liver and the pancreas both kind of use it. All right, so here's some pictures of the duodenum. I put these two side by side. There's the beginning of the duodenum there, then it goes retro, then it pops back intra. There it is there, you can get a full view of it. So what they did here is, they cut the next part of the intestine away. So it goes duodenum, jejunum, and then ileum. But they cut it away here, but you can kind of see the line it would fall. Okay. So imagine like you have a 21-foot long python, and you put it in a cloth bag. And then I take the cloth bag, and I got the python on the bottom, and I hold the cloth bag at the top. So in my analogy, the python is what? The small intestine. But as I'm gathering it up, like the cloth bag represents, in my analogy, the mesentery. And so do you see how you gather the cloth bag up? And it anchors to the back body wall. You noted it yesterday as the root of the mesentery. So imagine if you cut that off the back of the body wall. You see that cut you make from there to there? They're cutting the root of the mesentery off there. Okay, so I do want you to know that, because you're supposed to know the root of the mesentery. So all these intestines are bundled up, but they cut it away there. So that would be the end of the duodenum, or you can call it the beginning of the jejunum. And at some point, jejunum becomes the ileum. I don't even know where. But I know it's ileum when you get to there, because when you get to there, then that's, boom, large intestine. Okay. So that's the anatomy you got to know. Duodenum, then call that end of duodenum or beginning of jejunum. You get credit. But for sure, when you get down there, what is it? Ileum. Yeah, so that's what. Just keep in your head. Let's just go back and just look at duodenum isolated. We looked at that before. Here it is completely isolated and dissected. So it goes serosa, and then the longitudinal layer, then the circular layer. That looks like mucosa or submucosa, I'm not sure. But look at this. Look at how grooved the intestine is. This is the end of the stomach. Look at those grooves. So something you may not notice here is, let me, that's the stomach. It narrows into the pyloric region. And somewhere in there is a sphincter. It's a very powerful guard or gatekeeper, somewhere around here. Okay, that's our pyloric sphincter. On this picture, the pyloric sphincter is right this label, like that. Okay, but those longitudinal folds, they run this way, right? There's a little sphincter up here too, it's a weaker one. Imagine you're squeezing the bag on both ends and food sloshes back and forth as you have those waves of peristalsis that squirt a little past and retropulsion. Just kind of go back and forth. Now, what are those folds called? Rugae. Rugae, very good. Of the stomach, then he gets into the small intestine there, the duodenum, aren't that the same? We have these circular folds. You kind of go in a circle like that. And those circular folds are called plica. The full name is plica circularis. Circular folds. Okay. And there's a functional reason. when the food stuff, the chyme, arrived to the small intestine, you don't want it to slosh through real quick. You want to force it to spiral around to slow and increase its contact time. And what's going to happen in the intestine is there's peristalsis, but there's also segmentation, right? You first get more segmentation, which is a nice mixing. And then peristalsis happens a little bit later between meals to help move it forward. But basically, the plica help because the chyme increases its contact time because of the circular folds. It doesn't just slide right through. All right, well, anyways, there's the major duodenal papilla. It's receiving secretions from the bile duct and the major pancreatic duct. So let's say it's kind of like right in there. Major duodenal papilla, nipple-shaped. Major duodenal papilla. Okay, well, anyways, we got the bile duct. They call it common bile duct. I typically drop the common. Use green there. That's going up the biliary system. We'll talk about that later. Bile duct. But also you got the main pancreatic duct. See, I'll use blue. Main pancreatic duct. Remember, the liver and the pancreas, those are your two major accessory organs of digestion. And this is an exocrine function, right? You're secreting into the digestive tract all those pancreatic juices and all the bile to help emulsify fat. So they're squirting in right here, and you're spiraling around the chyme for nice slow contact. There's a lot of segmentation. You just mix it all up. So that's the anatomy there. Okay, more anatomy. There's two major blood vessels. Well, they cut them here, but I want you to know that the superior mesenteric artery and vein, they go over the duodenum. I won't try to draw them on my picture. Let's just note it. Let's see. So, superior mesenteric. A and B. So that's two, right? Just they got the same name. They're together. Goes over duodenum. There's another picture showing you the superior mesenteric artery and vein going over the duodenum. We have a nice dissection of it in our cadaver. I'll point it out to you. I believe our cadaver presentation is next week Friday, I believe. I'll have to double check the schedule. But anyway, more pictures of duodenum. Okay, on this picture, can you identify the duodenum? Just look. So yeah, that's it. Well, are you looking at that? Okay, good. And I point to SMA, superior mesenteric artery. There it is right there. It's going over there. It's going over the duodenum. Going over the duodenum. Just making sure you know that anatomy. Okay, so we got duodenum. What's this white band? Main pancreatic duct. So that's the pancreas right there. There's the pancreas right there. It's nestled in. Looks like an inverted tobacco pipe, and the head of the pancreas is nestled in the duodenum there. Okay, well anyways, let's move on. I'm pointing to it there. This is a backwards view. So if this is a different model, if this is an anterior view, that's more or less a posterior view. What you're looking at here are part of the colon there. But this is the duodenum. This is the beginning of it, retroperitoneal, and it pops out intraperitoneal. So this is superior mesenteric artery and vein. I'm not sure what 32 is. I'm going to have to work that out. Probably something you gotta know. Well, anyways, do you see superior mesenteric artery here? Boom and boom. Okay, what's that? That's the chyme. What if I have you identify the folds? That's the plica circularis and the folds here are rugae. You can begin to see the sphincter there. All right, so this celiac trunk is supplying blood to this region. And so, just to show it to you, when you cut off all the branches of it, it's simply just the first branch coming off the abdominal aorta. This is thoracic aorta, but as soon as it goes through the aortic hiatus, it becomes abdominal aorta. And so the first branch coming off is celiac trunk. The second branch is the superior mesenteric artery. Okay. So there it is again there. First branch coming off celiac trunk and superior mesenteric artery. There's also an inferior mesenteric artery there. So let me erase this. Here's abdominal aorta. Branches into two vessels, the common iliac arteries. Anyways, first branch coming off, second branch coming off, and third branch coming off down there. So that is celiac trunk. That one is superior mesenteric. That one is inferior mesenteric artery. These are single branches coming off. They're not paired. The branches of the celiac trunk, many of them are a study guide because they're providing blood to spleen, stomach, liver, all the things that we need to know. And so this is a good picture to study. Let's see here. So I'll just do the arteries. That's what this shows, no veins. So looks like you got celiac trunk coming off. Call number one, celiac trunk. It's going to give off a branch that goes off up and to the left. This one here, up and to the left, and it's following the lesser curvature of the stomach. So that's the left gastric artery. Number two, left gastric artery. There's another bigger branch that goes off to the left. You can see it behind the stomach there. It's going all the way to the spleen. So that was the splenic artery going off to the left. I'll just put two spleen. So that's our third branch there. The splenic artery. So those are the ones that go off to the left. Let's follow this one that goes off to the right. It's the common hepatic artery. Now the word common is very important because that means it's common to a few branches that you have to know. So it goes off to the right. Called number 4. Common hepatic. Does anyone know what hepatic usually refers to? Liver. Liver. Always remember liver, hepatic. Okay, well anyways, there's some branches that come off the common hepatic. Now this first one here, going down to the duodenum in the stomach, that first branch coming off and going down, that's called the gastroduodenal artery. I'll just draw a branch coming down, called number 5, gastroduodenal. There's another branch coming off, common hepatic. It's going to follow the curvature of the lesser of the curvature of the stomach, and it's going to anastomose with the left gastric artery. So this is the right gastric artery. Follows the lesser curvature of the stomach. So it's going to come off. Another branch coming off this way. This branch coming off, number 6, right gastric artery. Then, if you follow the rest of the artery up there, the rest of the way after it gets off those branches, just call it proper hepatic artery, or just hepatic artery is fine. I've seen some books call it that. Call that number 7. Well, it's going to liver, as you can see from the picture. So we'll call it proper hepatic artery. I put the proper in parentheses because it's not required you put proper. I think your book calls it proper hepatic artery. All right, let's talk about the branches that follow the greater curvature of the stomach. So there's a branch coming off gastroduodenal. So let's call that one, we're on number 8 now. That is what's on the right side. It's the right gastro-omental artery. Sometimes it's called epiploic, but I think your book calls it gastro-omental. Number 8. It's right gastro-omental artery. The left gastro-omental, which anastomosis would be, it's going to come off splenic artery right there. And right there. Number 9. Left gastro-omental artery. Give me a minute. I want to see what Meredith calls it. We call it epiploic or omental. I don't want to get a boatload of questions on that one. Actually, let me just look in the atlas. Standard there. Yeah, they call it gastro-omental in the atlas, so we're sticking with that one. So there's another picture you can study with the stomach removed, just so you can get a better view of the splenic artery. There's some side by side so you can compare, and there's a nice close-up one. This is a good spot for a break. When we come back, we'll talk about the pancreas.